Hey everyone, guess we'll get started here. Welcome to another episode of Common Lisp Study Group. I'm your host Ron Batum with Atlanta Functional Programming. Today we're going to be talking about Chapter 10 in Paradigms of Artificial Intelligence Programming Case Studies in Common Lisp. This chapter deals with more low-level efficiency issues and making more performant code inside Common Lisp, more so than the previous chapter, which kind of gave, sort of a high level, very quick way of actually getting to decent, I would say more best practices for actually writing out fairly efficient code in Common Lisp without having to go into some of the chapter issues that Chapter 10 talks about. Okay. So the stuff that we talked about, if you recall, with the memoization, compilation, being able to use the right data structures indexing, and finally stuff related to uh, um, what was it? Memoization, indexing, compilation, and I think there was one more. Um, there was actually, I believe that is it. Actually, um, yeah, that was it. Oh, and profiling and being able to actually profile your code and being able to write out appropriate statistics and being able to actually figure out your bottlenecks and speeding up your bottlenecks. All those are pretty standard techniques to optimize your code. That's not specific to Common Lisp actually. Choosing your own data structures and levels of indirection can be commonly associated with any programming language, particularly those that are statically compiled and have more efficient pointer access, which Common Lisp does provide, but through vectors and other data structures. Certainly in C++, for example, you have your standard template library data structures. Choosing the right data structure and being able to use that will give you semi efficient performing code, actually very performant code in the case of those languages. In Common Lisp, there's a little bit more that you need to end up doing to get to that to the level at which where they could say it's comparable with um, statically compiled language, particularly C, because remember the context in which Common Lisp kind of was optimized for its competition at the time that the language was standardized was effectively C, Fortran, Pascal. So the performance techniques that they've kind of adopted was to fit in that realm, so that they could get at least as fast as C in most cases. Okay, I'm being very precise in my words, just mainly because some folks and other folks will pick up, people say, "Oh, Common Lisp is has fast in C," and then give an example where it isn't as fast in C. It really depends on what you're trying to do. For a lot of application-specific use cases, Common Lisp is comparable, if not faster, than most of the languages that are on the market. I'm not going to say that the ecosystem has matured for all use cases that are out there, just mainly because, up until recently, some of the libraries that they picked up was more or less kind of in states where there are bugs, but it's mostly functional. And also for some use cases, for example, containerization and more of the more recent cloud kind of initiatives, Common Lisp kind of has not kind of built up its own tooling to allow you to interactively create, containers and actually hook into container runtimes and that sort of stuff. That said, a lot of the libraries that are around are extremely performant for most systems level use cases. And the purpose of Chapter 10 is to kind of go through some more additional, more lower level techniques that you can actually leverage to further speed up your code. Now, some of these techniques aren't are stuff that we've actually covered on in the study group before. Some at superficial levels, others semi deep dives, I would say, just mainly because at the time I wasn't as familiar with some of those concepts and I had to kind of do some trial and error. But today we're going to be covering some of these again, as well as other things that I may not have actually gone into as much depth as I would like to. And these are things that would cover. The first couple of things that we're going to end up covering mainly are going to be dealing with type declarations, avoiding user functions, and complex argument lists. And I think based on time permitting, within the next hour and the discussions that we'll have, not to mention my own little experimentations, we might cover the next three at a later time, which will require a little more of a deep diving, just mainly because of the fact that the topics there that are involved, especially the topic on compiler macros, I didn't really cover in as much depth as I would like to, and I would actually want to explore that topic a little bit more beyond of what the book actually covers, on top of avoiding unnecessary consing and again, data structure lookups, in which there's the stuff that the book covers in choosing the right data structure, and on top of what it advises, there are other libraries that we might be able to take advantage of and write some decent examples and case studies throughout the program. Before we dive too much into today's discussion, as usual, Atlanta, if you like our videos, please hit the bell icon and hit like and subscribe to the Atlanta Functional Programming YouTube channel for further updates as to whenever new material comes in beyond not only with the Common Lisp Study Group, but other topics that may arise. Additionally, Atlanta Functional Programming is looking for speakers. If you have a topic that you would like to talk about, I usually am a squatter on functional programming.slack, as well as Discord has Bugram. Um, and for those of you who are in the Tech for Atlanta Tech Slack workspace, you could also find me as Bugram there. Just reach out to me, DM me, give me your talk topics, and we will get them scheduled as soon as possible. Um, Additionally, those of you who are in the Atlanta area, um, AFP is looking for a new home for our in-person meetups. Please reach out to me or my co-organizer, Judd Taylor, via Meetup, and we will, probably reach out to you later on to see if we can look at your space and see if we could come up with something that would benefit both of us, your organization as well as the Atlanta Functional Programming Meetup. We're not specific to any programming language. We are trying to kind of promote Atlanta functional programming. Has functional programming has kind of a paradigm, a course complementary paradigm to all the existing paradigms that are out there, and so forth. We don't want to necessarily um, kind of discriminate to all of the languages, because every language nowadays have first class functions or have a roadmap to adding first class functions, and it would be useful for some of those techniques to come kind of into more active APIs beyond the ones that are currently being developed right now. So to begin today's discussion on um, type declarations, I'm going to begin with a very simple example here. And this is kind of pretty typical when you're dealing with kind of showing uh, types, all right? And starting with types performance. Okay, before we've talked about, we're doing sum, okay? And sum is pretty typical. You have defun, sum, and the book kind of covers some squares where it's just making it just a slightly more complicated than what you would normally have. Okay, so you will actually, sum a sequence of the square of a sequence of numbers. Sum the the sum of the square of each element of a sequence of numbers. And typically in this kind of example, you would start with something like this, okay? Although there are other ways writing it. I know for those of you who are watching, you're gonna immediately probably say, why don't you use loop? I'm not using loop for the time being. We could try some of the different techniques with adding type declarations to loop in a separate example after this. But this is kind of the book example that was there, just that I want to cover because it actually covers a lot more than just adding type declarations to like the integer counter and things like this. So, or even in the case of integers, just it allows us to add more type declarations that most people aren't necessarily familiar with. And in here, we could do times, okay, and we grab the counter, all right, which is just, for lack of thing better, it will just take the sequence and the number of gets the length of the sequence, and it runs this a number of times. Most people are familiar with the do times macro. This eventually converts into essentially a do form. And this is going to access each element inside of the sequence, and we end up being able to write, essentially an increment function. And this incf, for folks who've seeing this in the first time, is basically a set f with an increment. Um, and what this is doing is it's going to go ahead and grab um, the square of the element that we've just gotten, which we're going to use the element of the sequence API. And that just takes the sequence and the index, okay? And then after we're done, we just go ahead and return sum, okay? Pretty simple function. You can also define, obviously, square is, your standard square x, 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 okay? And let me just make sure something here. Describe square, because I just saw it in my REPL and I didn't define it before. Oh, it defines it. Let me go ahead, for lack of a, don't want our stuff when we're talking about vanilla Common Lisp to also include stuff that's in PAIP that I may not leverage. So let me just double check now here. Our square function, square. Let's see if that is Common square is undefined. Okay, so basically I've done the wrong thing. I accidentally interned that function. Now clear, and we just need to do apropos, not describe. And we see that there is no squares here. Okay, other than the SP kernel one. And if we describe square here, it's undefined. If we look at the symbol function of square, you'll see that symbol if it's not defined. Okay, so let's just go ahead and turn that. Okay, just to be in the case. Now let's go ahead and define our functions in our REPL here. So here we've defined square, and here we've defined some squares, and we could see square here. If we do square 2, we have 4, and if we do some squares of the loop for I up to 10 collecting I, this is just creating a quick range for us that we can leverage. It'll end up creating some squares 385. So far so good. You can see that this is actually going to this is a very generic function. We have seen this before. We've seen this written in many times. No big deal. But if we know that we're only going to be doing collections of the size of just integers or just fixed nums, okay, we can make it obviously a lot faster naturally. And we've talked about this when we were talking about um, uh, type declarations in the past, but I wanted to kind of bring up some of the stuff that I didn't really cover in those additional chapters, mainly when we're talking about arrays and some of the best practices, because there's a couple things in that was brought up in this section related to some types that you'd want to be aware of that I wanted to kind of cover beyond just fixed sums and floats, which we did cover. And this is kind of useful for us to at least do some sort of deep dive on. To begin with, let me just go ahead and add the basic type declarations with this, just to get the just some of the questions started if folks are wondering. To do some of the basic type declarations, most of you are aware, at least I hope, if you followed this along, that you define your type declarations with the declare form, okay? And the declare form actually takes in a couple of things, okay? It could declare, it could use, it can use already known types destructors, okay? So for example, since we're using fixed num, and we know that what's being passed into, say, um, actually, you know what? This probably will be better. Let me go ahead and create a different, no, I'll do it this way. Okay.
Hey, Rom, I'm not seeing your screen. I'm only seeing the
Oh, really? Okay, give me a second. Maybe I've forgotten to share my
purple.
screen correctly. Yes, I will go and share this. Uh, oop, do. Maybe I forgot. Yeah, I did. Sorry about that. This was on the
No
YouTube
problem.
channel, but I did forgot to share it subsequently on this channel. All right. Can people see it now?
Yes.
Okay. All right. Excellent. So where was I? Okay. So everyone knows about the declare form. We covered the basic primitives of stuff, and I think I may have covered this one thing, but just to kind of reiterate some stuff that does it. Effectively, for most of your primitives, there are already known um, uh, I guess you could say type constructors, but for lack of a better terms. Folk coming from Haskell, these are not I wouldn't necessarily say they're the same thing. Those who know better than me, please correct me if I'm wrong in the comments in the YouTube video, and I will certainly correct myself. But this is kind of like a alias. Okay, we've seen fixed sum before, we've seen float before. We're going to use this later on in some of our in our type declarations. But for now, what we're going to be using is we may not you may have not seen type before. I may not have covered type. And what type does is specifically it allows us to create a compound type, okay? And there are many known compound types, one of which that we're going to be using in this case is something called the simple array, okay? And simple array is different than, array. Simple array are one-dimensional arrays. Array, has in the array constructor, is a multi-dimensional. By default, is always a multi-dimensional array. So if you know that you're getting a sequence has a traditional um, array, all right, or using maybe the C++ parlance, a static vector, or actually a stood array. This simple array type constructor is what you would want to use rather than the uh, other array syntax because that's more general than this one is. And what you could do is here you could specify the type. In this case, we know what our type is going to be. It's going to be a fixed num. And our dimensions are not going to be defined here just because we are not doing a multi-dimensional simple array. Okay. We are actually going to go ahead and treat that as just a star. Okay. That just basically tells the underlying Common Lisp compiler you're going to have to do some digging into the um, the dimensions, but ideally it would be usually when you say simple array, they're thinking of a single dimension. If you're going to do more of the array syntax, and I'll go through this later on when we talk about the type constructors that are available, that Dr. Norvig kind of like recommends people to kind of use over many more complex types. This is something that would be useful to be aware of. So if you're using more multi-dimensional stuff, array is one of them. But if you're doing more single-dimensional stuff, simple array is what you want to use. Now, the last thing in this type constructor, on top of specifying the star, is naturally the arguments, as you could see there, the variables that represent this. And in this case, sequence is going to be the type variable that we are going to be specifying for actually telling the compiler to optimize. Now, this declare statement not only allows you to specify types, which will help optimize your code, you can actually tell it to take function pointers, right, or functions, Lisp functions that have been interned, in this case our square function which we're using in this code, and explicitly tell the compiler to inline this, okay, into the function. So I'm going to first do this kind of step by step because I want to see kind of the disassembly. The chapter goes through it separately, but I think it would be useful for us to look at uh, the inlining before, like a before and after with it. So bear with me. I'm going to go a little out of order with what the book kind of covered, but I think it will be it'll all make more sense when you start looking at the disassembly and the speed at which doing inlining is. Most people coming in from other languages, you, especially compiled languages, are probably aware of, some of the usefulness for inlining, but may not have seen kind of the ability to see the before and after, mainly because you would have to use additional tooling to actually go and see it in real time, because it affects the compile edit cycle that most people in statically compiled languages are familiar with. But here we have Common Lisp, we have interactive programming. Come on, let's use it while we can, right? Um, the final thing that I'm going to just briefly mention here is the optimize keyword. This is where you can add your optimize flags, okay? And you've seen some of these before. I've talked about speed, space, and safety. Um, and there are two others that are here. One is in ANSI Common Lisp, which is debug, and this is to ease debugging. So for folks who are coming from the world of release with debug symbols, this is kind of where speed and debug is used by the Python, the Steel Bank Common Lisp Python compiler. And I'm sorry if I have to spell it out that way, but it's because I know um, folks, when they hear the word Python nowadays, they're thinking of the language and not the actual Common Lisp compiler, which is named Python too. Um, but I know, unless you're in the Lisp community, you won't realize that SBCL's compiler is named Python. Anyway, um, for the purposes of the optimization discussion today, we're going to only focus on speed and safety. Okay. The other two, well, three in this case, uh, actually, I think compilation speed is also used in ANSI Common Lisp now. I gotta go double check that. I'm pulling up the hyperspec just briefly, just to double check here. Um, the hyperspec, and it is in, yes, compilation speed is mainly, again, as the name suggests, to deal with whether or not you need to deal with a fast compile. Now, naturally, um, we're not going to change that. We're going to keep compilation speed as a default for both, and we're going to deal with what's it? Um, uh, Debug also and space also has a default. But for speed, we're just going to specify it like this. This usually means we're going to be default, but at the same time, we want to deal with safety being 0. Now, you don't necessarily have to specify speed if you are not prioritizing it. But I believe in some Common Lisp compilers, if you say safety is 0, um, they might internally up the speed priority. So by specifying it this way, you're guaranteeing, I think, the default of 1 is going to be used. All right, so we're doing essentially -01 here with the safety checks being ignored. Okay. Naturally, now that we have this, we also have to, we can't alone do this. This is going to be a great type check. So if you end up giving it, a sequence of, say, floating point numbers, obviously the some squares will give you incorrect answers. It's because it's expecting a fixed num. And I think you even get a type error too as well internally when you try running it. But I'll show you. I had to have to think of a good example to actually define, so we can try that later on. But let's finish off adding the type declarations for the rest of this code. Naturally, since we're going to be dealing with fixed nums, we need to make sure our sum is a fixed num. All right. So and we are going to also add 2 additional flags because you have the counter variable there, right? We want that counter also to be dealt as a fixed num too, because this is going to essentially force the optimizer to take this into account too. So internally, it'll convert it into an appropriate pointer offset when it's trying to access the variable. All right. Um, and instead of element, what we're going to end up using is uh, a and as you can see here, just doing this, it'll still do a generic plus. Instead of using element, we're going to do 2 things. We're going to actually replace element with a um, array access, which is called SVRef. SVRef, if most of you have seen some of my earlier episodes have recalled, SVRef is kind of like aref. But it's for simple vectors. So naturally, if you're going to be dealing with and you want to prevent this warning, as you can see here, saying that we're going to have a generic plus operator here being used, you can access and force it to actually use um, simple vector reference to actually go in and deal with the um, pointer offset. This alone isn't going to get rid of the fixed num arithmetic because there isn't a promise that Square is going to actually provide you with a fixed num. Okay, but so we have to actually tell it that the return value of Square is a fixed num, and I'm going to just show you that this is the case. It's not you have to keep on adding and seeing kind of like what these costs are as you build it up. Okay, so you can see here it's you're getting an error. Wait. Did I? 1 second. Um, warning sequence drive sequences of value. Simple array fixed num conflict with a certain type. Simple vector. Okay, so is there a reason why? Um, okay, let me try one more thing. I think I'm gonna have to add the other one. So this here, this square needs to be. You need to tell the code that this is the return value of that value is going to be um, a fixed num. And to do that, we have in Common Lisp something called the DA special form. The DA special form is basically adding a the book calls it a promise. All right, you're basically telling the the um, compiler, yes, this is if the return value of this will always be a fixed num, so it always does the right thing. Um, and it's but I don't know if this is going to fix that warning. We'll see. Yeah, it's still going to be dealing with that. So why is simple array? So this used to okay. This is telling me that simple array fixed num star is not being liked. Let's see if I can use simple vector instead and see if that changes it. Okay. And what did I change now? First argument is a sequence, not a vector. Ah, so if I change this to simple, so that means this book, so there is something interesting about this. So the book's code is not, it's a little outdated in terms of what ANSI Common Lisp ended up adding. Okay. Um, Let me see if I add the array, let me see what happens here. And okay, so we're going to go ahead and keep that. That's a warning. It's going to end up having some slower code, but I'm guessing it's going to probably change when we add inlining of the square code into it. Maybe. I don't think so, but we'll see. Some squares. Do I have my previous example here? Yep, there we go. Aha. Okay. So, right, because of the fact that it got a sequence and it's not accessing this, so there must be some um, incorrect assembly created here. So let's look at this. Okay. Um, okay. Yeah, you see here it added these checks about the simple um, vector in the sequence because it kind of expected that. So instead, let me try changing this to aref, and since we're using a simple array for now, and I will change it to a simple vector later on to see the difference in the actual generated code. So let's do that instead, just to get the code kind of working. Okay. Okay. Let's just see. Ooh, sorry. What? Um, Fixnum I, the fixnum. Okay. There is a slight fixnum sum fixnum I and increment the fixnum square. Okay, so it's not liking maybe the fact that I didn't put the inline in here. Let's see. says that it was not saved. Let me see something here. I want to try something. If you, for folks who don't mind, that's kind of weird that it just did that. So let me say it. Do this. It's compiled. F. Square could not be inline because a global inline or XBT may be inline must be in effect to save function definitions for inlining. Okay, so I'm going to have to declare inline separately as a global function. So instead of doing this, I'm going to have to use a declaim. So again, this might be just because of the way the code is now written. Not a big deal. Declaim. I would have assumed that this would work, but we'll see. Okay. So let's do this one more time. I'm going to restart my Lisp just to kind of show you guys what this is doing. All right. Clear. Clear REPL. There we go. Okay. We first compile the code. Then we say that the square should always be inline. This is going to actually create the symbol and intern it. This is going to tell um, uh, Common Lisp that whenever it's being used, square should be inlined into the function. And this is going to go ahead and compile it, right? No, it does not. Interesting. This is in effect global inline function. So I'm gonna have to figure that out. That's kind of weird. I thought this is what I did correctly. Let's see here. Uh, Declare the top level optimize speed, box, sum square, do time, blah 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 blah. Caught style working. Call to Common Lisp Square could not be inline because its source code was not saved. Source code was not saved. Oh, because it was already compiled, it can't inline it. So I have to prevent it from actually compiling square. So when we load it, the symbol function only has the source code. Um, let's let me see. I'm forgetting right now. There's a way in Common Lisp to actually prevent your source code, in SBCL to prevent your source code from being compiled. And we need to leverage this in this particular case just so that when we do want to inline functions, we can inline them. So I just got to go look this up again just to remind myself. My apologies. Common Lisp prevent compile for inlining. Source code. And what this will do is there we go. Okay, so we're gonna have to do this just for the time being. We're gonna have to do, instead of inline, we have to say not inline in general. I don't know if this is gonna work. I may have to restart my You know what? I'm just going to restart it again just to unintern everything. I'll show later the experiment to see if we need to restart it, but just so that we can actually see if this works the first time. If I do this, um, and I compile it, okay, and now here locally, if I do inline square, see what happens. Source code did not load, did not save. Um, okay, so I need to actually also specify one more thing. Debug has to be also turned on. It looks like in otherwise the source code is not going to be defined. Okay, so let's do that. Unintern square. Try this again. I'm going to wrap this whole thing. CP slurp F. Okay, and F. Okay, so now everything is here. We're going to make this into what's called a locally form, and this is going to just define this all in one fell swoop. And here we're also going to turn on, you know what, actually I don't think I need this to be local. I just need to probably do, no, this is fine. What I need to do is also say optimize debug 1. Okay, so let's see that. Okay, let's try this now. Let me just double check to make sure that the unintern actually happened successfully. Square, and we should get common. Yeah, that's fine. Good. Visual R. Okay, let's try this now. R, and did it happen? No, did not actually do what I expected it to do. That's interesting. So this is particularly interesting mainly because the fact that I guess the um the SBCL code by default, you have to go out of your way to make a compiled function not compile and retain its source code information, which is kind of weird because I would think that that kind of breaks the idea of what yeah, I thought that's what I did correctly. Um, the declaration line replaces function call and function. The Common Lisp Cookbook also kind of teaches you um, uh, what to do. Um, it's kind of weird though that it's not actually doing what I expect it to do. Function calls replace with the function body if the compiler support lists it will lost function calls. Best situation to use inline might be those small but frequently used functions. Um, yeah, maybe SBCL doesn't support function. I thought it supported function line. Common Lisp. Common Lisp function inlining. Um, is okay. So we're gonna probably have to do something like this. I hope this is not the way to do it. Um, so let's try this twice. Okay. Instead of doing this, let me try this one more time. Where is that uninterned? Okay, let's try this again. I was kind of right that I need to use inline here, but I'm guessing I'm gonna also have to specify um, okay, so then what we could do here, maybe do that. So this is going to actually do, not declaim, sorry. No, it is declaim because that's a global declaration. So we do this, sorry, that. Okay, now here we have another, ooh, that looks promising. Let me do that one more time. Just making sure, describe square, good. So what we may have had to do is create inline square so it keeps track of that, and then we got to kind of also specify inline square here as being, hey, you need to inline this function because we retained its source code information. R, yeah, and then it will actually do what we expect it to do. So hopefully here, if all goes well, let's see if my sum squares work. No. Why is that? I see. Let's see. The only thing left is I created a collection. ELT. ELT is sequence index. Aref is a sequence and subscripts. So why is that not working? Hold on. Let me check something here. Loop for I up to 10. I think I might be using the wrong access for this sequence, but I thought aref would work for both. Collecting I. First grab that and then do aref star 3. There we go. That's the reason. Okay. It's just not um, doing what I expected to. So what I have to do is I have to do make array. Make array. Let's just say 10. Okay, and initial element is going to be initial contents. Let's just go ahead and say contents. Okay. Oh wait, I might be doing this wrong. In loop, I thought that there was a way to make a vector. Make. I'm having a brain fart right now. SBCL. This is just going to create a filter vector. Yeah, you know what? Forget it. Initial contents is going to be loop. Yeah, I could probably do it this way. Loop for I up to 10, collecting I. Done. Oops. What's this? There are 11 elements. Oh, sorry. There we go. That's right. Now I can actually do this. Some squares. See if this works. And we get our 385. Okay. It's kind of weird because what's happening is and this actually makes sense. Um, the reason why before the loop wasn't giving us any, this kind of goes back to some of the problems with some of this low level efficiency stuff. Um, in typical languages, what you would get, like in statically compiled languages, let's talk about statically compiled languages. Um, when you're providing type hints and you compile a function, it would recognize that you're passing an invalid collection type of the type that it's expecting, and then it'll throw a type error. In Common Lisp, if you have safety turned on, you would end up seeing the following. Okay, so if we actually go here and say, instead of safety off, let's just say speed and safety, okay, which is naturally going to be the typical situation. Both of them are set to defaults, and um, and so forth. So we'll go ahead and recompile this. If you build and then run this here, not this, sorry, our original call, you'll end up getting the following error, which is that the argument that's passed in is not of type simple array, okay? Which is what we would be expecting, a type check, right? But because we said, hey, I know that I'm going to be always passing in the right thing, which clearly I've forgotten that there's a when I said that it's going to be a simple array, I should have made it a make array. My apologies for that. It kind of also illustrates what this, so it's kind of a benefit for both of us. Um, the compiler recognizes that you know what you're doing, and it gets rid of all of these checks that you're seeing, like this type error stuff that here, because these are conditions, and it tries to optimize the code as much as possible. And so what it does instead is because it couldn't access that pointer, and you saw what it did. It basically gave you no access to it, and it just returned sum equals 0, which is because sum was initialized to 0, right? So this is kind of an expected benefit and a curse of using this. But if you're actually leveraging um, type declarations, this is kind of some of the stuff that you will end up encountering if you're not careful with leveraging some of this stuff and knowing fully well what you're actually optimizing for. Okay, but once you do optimize the hell out of it, you can actually get some interesting um, uh, code generation. So let's actually look at the code generation. Okay, this is, I think, is a an important piece of the puzzle. The disassembly that I kind of talked you through earlier is kind of similar of what you would encounter. Um, I think for the sake of example, it might be better to simplify not the code that we're looking at, but even trying the standard um, uh, code that of checking out the add function. And I think I've done this one too, and before in the past. But I wanted to kind of reiterate, what the differences are. Um, to review, we've all seen our standard plus xy function, okay, of adding it, creating it, and then doing a disassembly of this. And what this is going to show us is in a standard xy function, um, some ideas on how this code will probably look like. The main thing that you're going to see here is, in the standard code, and hopefully folks who are watching can see my highlight. Um, the first four instructions here are more or less creating the stack frame before calling um, the generic plus function. And this is a very expensive function. The reason why it's very expensive is because internally it's trying to figure out, well, what are these two types? Are they compatible with each other? If they're not compatible with each other, let's go ahead and throw a type error. In that condition stuff that I was showing that you saw earlier, that's essentially some of the stuff that you will see here. It will also potentially create some additional variables behind the scenes. Okay. Um, plus is a very generic operator in uh, Common Lisp, and in fact, just to for full disclosure, later on in this chapter, we actually talk about avoiding some of these kinds of functions by adding some of these type declarations. Okay. Um, additionally, though, it's not fully optimized, right? Um, this could actually be further optimized if you provide not only hints to the compiler, but also provide so the permission. I guess is probably the best way to say it, for it to ignore all safety together, like we saw earlier, and just run as fast as possible. Okay, just create as the most efficient code as things. So to do this, we have to do a couple of things. One, obviously, before we need to, because we're only going to be dealing with fixed-sums for this example, we're going to go ahead and set these two arguments to both be fixed sum. Additionally, we're going to also add the optimize flag to optimize for no safety, okay, and for speed, okay, which I should have brought this up earlier, but I'm going to bring it up now. You may be noticing these zeros and ones to speed and safety and debug, and you're wondering what the hell these numbers mean. Um, the optimized declaration, according to the hyperspec, and the book covers this a little bit, essentially uses a priority listing of flags to determine what to actually prioritize when generating code. Okay, this will allow it to make certain decisions, um, uh, as well as uh, keep certain compilation pipe paths from occurring to generate the kind of code that you expect. Okay. The priority is from 0 to 3, 0 being least important, 3 being most important. Um, default is 1 for all of them, which means they're all equally important. And naturally, it's you want to use one versus the other. I forgot to mention one thing I noticed in my notes that I about inlining, but I'm sure most of you know this anyway. The same problems that you have with inlining functions in most statically compiled languages apply here, and that is mainly if you redefine um, a function that has been inlined, you have to go and recompile all the functions that call it, mainly so that they get the newer code. Otherwise, they will have the old version of the code. And remember, this is an interactive compiler. Um, you don't necessarily have it recognized when you've redefined an inline function. You have to actually, it doesn't just trigger an automatic compile of all functions that depend on it. And so you're going to have to just be cognizant of doing that when you're dealing with function inlining. Um, so we're going to go and speed this up. And this other point is that I want to kind of also bring up when I generate this code here that I think it's important is what the result of this code is and why it's doing what it's doing. Let me first compile this and then I'm going to show you the disassembly of this too as well. And then I will kind of bring up something that about uh, these types that become that's important when you're dealing with declaring types inside Common Lisp. All right, so you could see by just adding the Common Lisp the to type declarations and automatically telling the compiler just throw safety out the window, we've effectively shrunk first the number of instructions that we would normally deal with, okay, which is about 32 bytes, which dealt with creating a stack frame, calling the generic operate function, and then moving stuff around to actually get the return value. Instead, you told um, the compiler just use the add instruction, all right, and it will make sure that RDX and RDI both contain two fixed num values that it can actually go and add, um, and um, and it will do the right thing and have the return value associated with them. Which brings up a very interesting point about these type declarations that again I went out of order than if folks are listening following in the book mainly because I felt the assembly would kind of illustrate this piece. Um, Outside of the runtime type checks that we were talking about earlier, and I kind of illustrated with the example of with the sequence example for some squares. Um, Type declarations particularly allow Common Lisp compilers to choose the most efficient representation of data objects. Typically, most objects in a dynamically typed languages, and Common Lisp is, the first of all dynamically typed languages, um, support both, uh, and I'm pretty sure actually Python also supports this, box and unboxed representation of data objects. Okay, and box representations, those of you who are familiar with languages like .NET or Java, are essentially representations of an object that hold enough information regarding the type that the object underlying represents. Okay, this is very different from statically compiled languages because most of the time you're dealing with raw bits. So most of the time, the statically compiled languages end up leveraging unboxed representations of types and allows them to optimize against those types. Now, there is an example here that I don't that I want to cover, but since there's about 14 minutes left, I don't think I'll have time. So I'll probably take a little bit of time next time to kind of cover this. There's an example here where the book covers about creating a multi-dimensional, well, a two-dimensional array of values and essentially setting all the values in that two-dimensional matrix to zero. And with the flags that they provided, the code that actually gets generated, the book was talking about using effectively what's it, Allegro in 1991. All right. So Allegro Common Lisp 1991 generated code that's very effective, comparable to C. I would say that it's probably have figured out better ways to make it even faster than most standard C compilers, but has much as Lisp is innovating, other languages compilers are innovating. So either way, they might be kind of at the law of diminishing return sort of a stage. The book example, and I'm just going to briefly kind of show you what this looks like, is nothing more than first adding an optimized flag here of speed 3. I think it was safety 0. And here we also specify um, one more declaration, which is type, and we're going to say that our it's going to be a simple array, I believe. Yeah, simple array of single floats. And the dimensions are going to be, in this case, 1024 by 1024. Okay. I believe I have to do it right. This is the notation, right? I think. Yeah, 1024 by 1024. And we'll use ARR here. Oh, wait. My apologies. Okay, so we don't need any other things. And we do times I 1024 because we know that we're dealing with a very fixed size array. And we do times here for j 1024. Oh, sorry. 24, and we just go ahead and do setf aref arr ij 0.0. Okay, now this code here is if we actually go and look at the disassembly, and next time I'm going to actually show the C version when we do optimize 3, just to see what the difference is between GCC and this guy. It would be pretty neat to kind of compare and contrast this. Clear array. Okay. And what this does is it, and this isn't, again, we are still having this like invalid index array error that we can also get rid of by promising some additional information to clear the compiler. So for example, this guy here can say we know that this is going to be declared fixnum ij, and let's go ahead and say that this guy we know is going to be, I think, the fixnum. And actually, this is not going to be the fixnum because this is a pointer reference here. We want this guy to be a def fixnum, but we need also array access here. Okay, this is done. Let's see what the difference is here. This is 112 bytes. Let me see if I made it slightly better. And I'm trying to get rid of that call there, that invalid array index error there, because it should technically be not necessary for this, but we will see. Clear array. Nope, that still didn't work. Okay, I guess we can't necessarily get rid of that because it is the guaranteed safety net that's needed for accessing something from within an array itself to make sure that so this is for, one of these is for I and one of these is for J. So I think the innermost one, this is at A9L4, is going to be related to J, and the L5 one is related to I. Okay, so in the last 8 minutes, I'm just going to briefly cover kind of some of the best practices that, or common declarations that he felt. And next time, I'm going to just briefly take some time to talk about the C optimization example, just because I thought it would be cool to actually cover it. Just didn't get time to actually do that. So in PAIP, of all the declarations that are available, and there are a lot of them, you could also do user-defined declarations in Common Lisp. Um, the he suggested that the following should be taken kind of into some deep consideration if you're trying to deal with low-level issues. The first set of declarations is naturally fixed num. You've seen this enough times in this example and this discussion that fixed num is probably already on the top of your um, list. On top of that, originally at the time that the standard was created, float was another option. But in newer Common Lisp development environments, I would say that float has been split properly into single float and double float to represent single precision, double precision appropriately. Um, there are other types of numerical declarations available at your disposal, um, but some of them do not necessarily help the compiler to speed up code. Um, one is on top of fixed num. Okay, so hold on, let me just pull up single float and double float are the ones. There are ones that don't necessarily help the compiler. These will. These listings here help the compiler. You might so one of the things that doesn't help the compiler is the following. Integers. Now you might be surprised by this, but for folks coming in from other languages. But in Common Lisp, integers do not just include fixed nums. It also includes big nums. Big nums are proper integers in Common Lisp, and that's how the integer promotion pipeline actually comes in. With if you're using say plus, the generic plus operator, it automatically promotes it, so an integer can become a big num without you having to actually go and explicitly call it out. And since big nums themselves are objects that might be particularly complex depending upon the Common Lisp implementation, it almost always will leverage the general purpose add versus using um, the add instruction. So it will become expensive over time depending upon the type of system and type of work that you're doing. Now, that said, I'm not saying that big nums are useless for folks listening in, okay? It's just that for low level efficiency, you will end up incurring some level of cost if you use big nums almost exclusively in your code. Um, at least that's what I understood in this book, and in other books on just using big nums in general. Another thing is that he points out is using list and array versions for all of the commonly used sequence functions. Um, Now, some of this might be dated, um, but I'm pretty sure most modern systems still do this. There are separate functions for list and sequence versions for all of the sequence functions. And so um, if you know um, that a particular argument to a function is either a list or array, to force it to use that appropriate array specific or list specific sequence function, you must declare your arguments like we did earlier with simple array has uh, list or arrays. Um, so so we have now list, array, fixed nums, all those primitives here. Another set is simple vector and simple array. Now the book defines this, and Hyperspec defines simple vectors, simple arrays as those data structures that do not share structure with other arrays. Additionally, they uh, it mentions that they should not have fill pointers, and more importantly, and this is very very important, they are not adjustable, which means unlike folks coming in from other languages, particularly stood vector folks who might end up thinking that having a reallocation is going to happen here and still create efficient code. Here, um, the in Common Lisp for certain optimizations to occur, not having an adjustable vector will result in very, very efficient code. Um, it is um, it is mentioned here, and I don't know if this is still true, that aref access of a simple vector is faster than a regular adjustable vector, um, and it's also aref is definitely faster than using the generic element operation, the ELT form of a sequence of an unknown type. Okay, so using simple vector and simple array will also result in very efficient code. The last two things that I want to kind of briefly mention is what I also kind of alluded to earlier is array and specifically array star dimensions. Okay, so we've actually seen this with simple array earlier, but array is the more specialized one um, than simple array. But array allows some of the stuff that we've talked about, the adjustability, the fill pointers, and so forth. Um, it also can take half the storage. So um, if you end up if you specify a general array using the actual appropriate array elements, knowing that they're all going to be of the same type, um, the allocation scheme behind the default Common Lisp compiler will do the right thing. So, for example, if you know that you're going to deal with an array of short floats, um, it will make sure that it allocs an array that is half the storage of a general array, which is going to be the size of a float or size of an integer, which is I think 8 bytes now on a 64-bit architecture. Um, It also would allow instruction selection to be better because it will recognize um, that since these are all the same type, and if they are using, say, floats in the example that I mentioned, to choose the floating point instructions versus using the generic operation to determine which code is good. So you end up getting more efficient code here. Uh, and the array dimensions that I kind of specified earlier is also very, very useful. Um, this one is also going to be dealing with mainly multi-dimensional arrays. That syntax that I just showed you there with the array star dimensions is kind of the full form of the array or simple array type specifier. So you kind of already seen this in the example that I kind of showed you with the clear M array, where you have this simple array. You just need to change a simple array to array, and you have the adjustability and the floating point. But again, the difference between simple array and array gives you uh, does inform the compiler to choose more generic versus more specific instructions. So be cognizant of that and do the profiling when necessary. Um, yeah, I was hoping that I would touch base with this here very quickly, but yeah, I think I could probably just mention this one thing. So the second thing that this chapter kind of covered regarding avoiding generic functions is more or less what we covered with declarations. I will kind of cover this very quickly next time. This is something that we've already kind of covered as part of this this section on type declarations, but um, given the fact that the book kind of covers it, I it might be useful to kind of mention it just for a brief moment before we start talking about um, using next time on talking about complex argument lists and the rest of the chapter. So that's it for tonight. Thank you all for sticking around. Are there any questions? All right. thank you all for joining. I wish you all a great evening, and I will see you next week.